If you want to start recording.
Yep, got it going now.
Awesome. Okay. So welcome everybody to our Tuesday talks, and today we are honored to have Semechah Louis, who is the professor of applied geophysics at the University of Toronto, Mississauga, and she teaches upcoming seismology course and the geophysics, as well as the introductory ERS 101. So Semechah, if you want to take it off from here, feel
Sure.
free.
Yeah.
Sounds
Thanks
good.
for the introduction. And let me share screen first, right? Let's see. Okay. So can everybody see my screen with the PowerPoint?
Yep.
Okay, great. Okay, so, oops, I should swap. Is this better now? It's a full screen,
Yeah.
right? Okay, great.
Yeah, that's great.
Okay, so yeah, thanks for the introduction. And I want to thank the committee, especially for inviting me here. I think my last time joining the club meeting is in 2018 when I first arrived. So it's great that, I can be here again. So today I'm going to talk about exploring earthquakes through the lens of geophysicists. And earthquake is not an unfamiliar topic to many of us because we always see it on the news. And in fact, there were two, I think, magnitude above 6 earthquakes that occurred yesterday, one in Russia and the other one in South America. But I guess today what I want to talk about is how, as an earthquake physicist, we try to use different geophysical tools to understand this, one of the most destructive natural hazards in the world. So, but before I jump into research, I just want to, I just want to introduce a little about myself and share a little bit about my background and education. And so some of you probably know that I grew up in Hong Kong, one of the most crowded city in Asia. So I grew up there. I finished high school before moving to the US for my post-secondary studies. So my undergrad and my graduate studies. So these are like buildings that I've spent like almost 10 years in. This is like the bottom one is the Earth Science Department at the University of Michigan. So I did my geology undergraduate degree right there in Ann Arbor. And then I moved to California for my PhD in seismology at Caltech. And these few pictures are, I guess I would just use, yeah. And these other few pictures are field trips that I was fortunately joining during, my school study. So the perks of, doing a geology degree is that you get to visit many beautiful places in the world. And so this is in Wyoming, looking out to the Snake River. This is in Iceland, actually, one of the most memorable trips that I have had. And this is during a field trip in California. And this is actually, guess where this is? This is actually one of the country parks in Hong Kong. So I think most of the people have the impression that, Hong Kong looks like this, is a concrete jungle. But actually, I'm, purposely posting this, sharing this picture because there are a lot of cool geology in Hong Kong as well. So in 2018, I finally joined UTM for my position here. And so let's get back into earthquakes. And so if you look at this global seismicity map, you'll see that there is where the earthquake located is a good resemblance of the tectonic plates map. And so, of course, you can see the difference along these boundaries. So for example, if you're at a convergent plate boundary, you will see that the colors of these earthquakes is a lot more abundant. So the colors of these points indicates the depth of these earthquakes, indicating that the earthquakes at subduction zone or at convergent plate boundaries has a much wider range of depths compared to earthquakes at, say, mid-oceanic ridge, which is the divergent plate boundaries. But basically, the resemblance between the seismicity map and the tectonic plate map is because earthquake occurs of two blocks sliding across along each other or interacting with each other. And so on the surface of the earth, the biggest, fault surface that you can find would be the boundaries between, major plates. And so what exactly happens during an earthquake? Earthquake is actually, a sudden slip, a very sudden slip on a fault. And so this is one of my favorite illustration of an earthquake. So this is a cross section that you're seeing here of a subduction zone where the oceanic plate is subducting beneath the continental plate. And you can see that this is the sliding fault surface with most of it sliding, but part of it's being locked. You'll see it as soon as I play the little movie clip. And so during the interseismic period, you can see that the sliding, the crust keep subducting beneath the continental crust, and there's stress building up in this locked region. And as soon as it exceeded the threshold, you'll see that there's an elastic rebound of the continental plate, which is actually the earthquake itself. And you can see also that in this case, it displaces a column of water that propagates landward and causes a huge tsunami. So this is a general, idea of what happened during an earthquake. So why are we still studying earthquake in that sense? It seems that we know how it happened. But the thing is, there are a lot of complex processes that is different from earthquakes to earthquakes, and a lot of them still surprises us. So for example, almost 10 years ago, actually, in March 2011, you probably still remember there is a magnitude 9.1 earthquake in Japan, towards the northern part off the coast of Japan in the subduction zone. And this earthquake, what makes it so unexpected is that it generated a large tsunami that devastated the coastal area. And in my opinion, Japan is like one of the best countries in terms of earthquake research and seismic hazard preparedness. And so they're not unprepared for any big earthquakes. In fact, they're really prepared. But what is unexpected is that they didn't expect such a large earthquake occurring in this part of the subduction zone. So what I'm saying is that they have done analysis and all kinds of forecasting, and all they have predicted is the maximum magnitude of earthquakes that is possible in this region is smaller than 9.1. And so they have built walls to tackle tsunami, but the walls are not high enough. And so water still, go past the wall and actually reaches the coastal area and even like damage a nuclear plant. And so earthquake processes surprise us still. And on the other hand, we also have other challenges. So for example, in recent years, we have all kinds of induced earthquakes. So these are caused by what we believe man-made human activities. And one of the great examples would be in the central US. So this is basically the seismicity, the cumulative seismicity in the central US between 1973 and 2015. And this is then showing the number of earthquakes with magnitude larger than 3. And what you can see here is that before 2008, the cumulative number of earthquakes basically increases pretty steadily. But after 2009, it really took off and shoot up to almost like 2,400 within the past 10 years. And so what people find is that these seismicity correlates really well in terms of both space and time with all the wastewater injection operations in this in those few states. And so this is like yet another challenge because now we're introducing external factors apart from just tectonic loading. And so what makes earthquakes so challenging to study? So first of all, I've already explained, earthquake process is complex. So each earthquake itself, occurs on a different fault with a different size. The mechanism is different, and so you cannot just study one earthquake and to understand all of them. And secondly, there's really no direct observations. What I mean is that, the crust is opaque, so we cannot directly observe the rupture, the slip on the fault. We just rely on data that we can record from stations on the surface of the Earth. And so the third one is there is really no precursory signals that we can identify to this point. And so earthquake itself is a sudden and abrupt process, and without any precursory signals, it's really hard to design any mitigation plan to avoid any kind of huge destruction. And so when we talk about like studying earthquake, what are we actually talking about? We're actually talking about like characterizing the earthquake sources themselves. So basically to understand how the rupture process goes, how big is the earthquake itself? What kind of, what's the amount of stress that is released from a particular earthquake? And we also want to understand not just the earthquake process itself, but also the cause and the aftermath of the earthquake. So what is happening leading up to that earthquake? And also, after an earthquake arrests, does it mean that the fault has come to a full stop? Or is the fault still, moving in some ways that we were not aware of? And most importantly, we are also characterizing the ground motion response as the seismic waves that is generated from the source propagates to the surface and generates all kinds of shaking. And this is directly related to seismic hazard mitigation. And so this also brings us from science to what I called applied science. It's to turn what we learn from earthquake source physics into formulating hazard mitigation plans. So one example that we have would be the earthquake early warning system. So many of you might have heard about it. It's basically to use take advantage of the time gap between the first arrival of seismic waves and the secondary arrivals, which is much stronger, and using just the first arrival waves to determine how big this earthquake would be and what kind of shaking it would generate with the secondary arrivals. And so within that time gap, the current plan is that we will send out warnings to communities in regions that will be affected, to warn them ahead of time. You may have, how many number of seconds before you will feel, this amount of shaking. And so that people have, at least a little bit amount of time to get prepared. So this is all about, like why we want to learn about earthquakes. And so to get into, a little bit about my own research, I try to understand, how and why earthquake occurs. And the approaches that I use is what I call the data-driven approach and the model-driven approach. And what I mean by data-driven approach is that I use seismic data that is recorded by dense seismic array to infer, earthquake source and earthquake paths. So question that I would be able to answer using this approach is that, for example, can we constrain earthquake source information in real time? So for example, if I have, stations recording incoming real-time earthquake seismic waves with just 3 seconds of waveforms, can I constrain, the properties of this earthquake? And also, what is the focal depth of an earthquake, for example? These are questions that I can answer based on observational data. But then on the other hand, I'm also using model-driven data, so which complements the observational side of things. Here we use physics-based numerical model to explain what is inferred from the data. So for example, if we say, these two earthquakes seems to be interacting with each other, one always occur after the other one happen. And what kind of mechanism is, causing this kind of so-called interaction? And for this type of questions, we will be relying on modeling approach to answer the question about like, why do they happen, right? So questions such as, what are the physical mechanisms that causes the earthquake to interact? Or how does pore fluid influence motions on a fault? These are things that we can model using numerical approach. And so in the end, we would actually go back to, our observational data. Once we build this, numerical model, we'll try to look at, compare our results with observational data and to see whether they match and whether the model is actually accurately describing what's happening in the field. And then we keep like looping to perfect our model in the end. So today, actually, I'm going to jump into one of my studies, which is trying to answer this question: how does pore fluid influence motions of a fault? And so if you are if you're familiar with the topic of induced seismicity, you know that a lot of them are caused by fluid injection into the subsurface. Especially, some of the largest earthquakes in the state of Oklahoma in the US is associated with wastewater disposal. And these earthquakes can reach up to, magnitude 5.8. So it's really, capable of doing a lot of damage. So people study like, why do they happen? Like, why does it happen? Why does fluid generates, triggers earthquake? And one classic explanation of the triggering mechanism is the increase in pore pressure along the fault, which basically shown by this diagram. You have a well and you have the injection of fluid into the crust. And when fluid actually diffuse in this permeable reservoir, it reaches nearby fault zones and increase the pore pressure along the fault. And if you imagine, basically your pressure of the fluid along this fault zone is increasing in pressure. So it's basically making the fault less clamped as it's pushing against the two sides. And so it lowers the fault strength and causes seismic slip. So this is what we think is a classic explanation. It directly causes, earthquake on these faults because of increasing pore pressure. But more recent study also suggests more complex triggering mechanisms. So the pore fluid may, be increased on faults nearby, but they didn't actually directly trigger earthquakes themselves. They actually induces a lot of aseismic slip. So what I mean by aseismic slip is slip on the fault that is, you can imagine it as creeping. So these are much slower movement, which is not capable of generating seismic waves. So you won't be able to record these from, seismic stations. But they do happen, and and with the right instrumentations, you can actually record the movements of faults, these little movements. So this is an example, a study by a group in 2015, where they found that these are the injection wells on the surface. They injected fluid into the subsurface, and these injection actually induces aseismic slip on this nearby normal fault. But afterwards, a little later, they actually see the major, earthquake that occurs in a strike slip fault that is a little deeper compared to the normal fault. And so what they see is that there's now an indirect, cause. The pressure, the fluid pressure actually triggers the aseismic slip first before triggering the major earthquake. And so what we're trying to study here is how fluid pressure induced aseismic slip can modulate earthquake timing. So what I'm talking about here is this is a typical, stress versus time figure that you would imagine for a typical fault that is capable of generating earthquakes. So what it means is that on the fault, the stress just keeps building up until it reaches a failure threshold. And so an earthquake would happen, a sudden slip, which releases a lot of stress that causes this vertical, decrease. And then afterwards, the fault will start building up stresses again due to tectonic loading. And so you experience this cycles of, stress buildup and release. And this is what we call the typical earthquake cycle. But what we're trying to understand is if we have this kind of fluid pressure perturbation, whether we would see, this typical, sequence being perturbed as well. So for example, are we going to see the advancement of the next earthquake if we perturb the fault with an increase in pore pressure? Is that possible? Or is it also possible that the increase in pore pressure can also potentially delay the next earthquake from happening? And so the typical idea would be, it would be it would be advancing the next earthquake because you increase the pore pressure. And as I explained earlier, you are making the fault, lowering the fault strength. But what we find is actually a little bit surprising. So before I jump into the results, let's talk about, how we do the study. So this part of the study is done with numerical modeling. So we first have to build a numerical model to simulate, these frictional sliding on faults. So first question would be, we need to find a good friction law that can describe what is happening on the fault, right? And be able to describe all kinds of motions. So this is, imagining this is the fault interface. The fault is under, compressional stress and also shear stress. And we need to find, what kind of factors that are affecting the friction on the fault. And so when we think about motions on the fault, I've actually already introduced the topic a little bit. We are talking about two separate categories of motion. One is, the earthquake itself, when the fault is experiencing very sudden, abrupt slip and a large amount of slip as well. But on the other hand, we are also, the fault can also experience very slow creeping motion. And so this is what we understand as friction strengthening behavior. What it means is that if the fault tries to slip faster, the friction actually also increases, making it actually hard to further slip faster. And so what it means is that as I try to slip faster, the fault will actually suppress the slip from going faster. And this is what I mean by a steady creep motion. So the fault will always be in this stable motion as shown by the turtle right here. It's pulling the the weight together with him through time. But then there's also another kind of, behavior, which is friction weakening, which means that, the faster you're trying to slip, the friction on the fault actually lowers, which promotes the slip to go even faster. So in this case, you would see the fault is either locked or it is experiencing a dynamic rupture. So again, here you can see that the turtle is pulling the weight stays stationary for a long period of time before actually moving in a sudden, manner. And so we need a friction law that is able to describe both types of motions. And so the answer is here. It's an empirically derived friction law, which we call the rate and state friction. So it's dependent on both, the slip rate on the fault and also the state, like the status of the fault, which, it's more related to like the materials and how the materials on the fault interface evolve through time. But basically, the perks of this law is that it's capable of describing a wide range of slip velocities, ranging from, background tectonic loading rate on the order of 10 to the minus 9 meters per second, all the way to seismic ranges, so up to like meters per second. And so I'm not going into the detail of this equation, but basically I want to highlight that this A minus B parameters is describing what I talked about just now with the velocity strengthening and the velocity weakening behavior. So depending on the value of this A minus B parameter, we will be able to see, some parts of the fault that is frictional weakening and some part is frictional strengthening. And so the methods here is basically we have lab-derived fault constitutive behavior. So we understand how the fault moves, in laboratory settings, and then we design friction laws to describe these kind of motions. And then we implement these friction laws into simplified models with tectonic, slow tectonic loading. So what you're looking at here is like the interface on the fault itself. And you can imagine that the fault is loaded by, tectonic movement on the side. And we are trying to study what is happening along the fault. Oops, sorry. And then we implement, this whole model and put it into a supercomputer to run the simulations. And what we get would be spontaneous fault motions throughout like all the cycles over cycle, and we would get sequences of earthquakes with resolving like all stages of slip during the interseismic period. And then actually eventually we, based on the results, we further refine our model or the friction laws. So this is the method, like what numerical modeling is about. And so we get into like a little bit about the fault that we have in this, particular study. So again, we are trying to understand, how the fault responds to pore pressure. So pore pressure change. So what we are modeling here is we assume that there's a fault close to a injection well, and there is, it's under the influence of pore pressure. And the fault is also seismogenic, has a seismogenic region surrounded by creeping interface. So to basically translate this into our model under rate and state friction, we have a fault with a large velocity strengthening area, but with a velocity weakening area embedded in it. And the fault is loaded by background plate rate. And so basically what you're seeing here is a velocity weakening area and how it's changing through time. And so these are just snapshots showing that sometimes the fault is completely locked in this velocity weakening region, but other times, it's creeping, picking up in slip rate. This color scale here indicates the slip rate on the fault. So with dark blue, it indicates pretty locked region. And with dark red, it indicates that the fault is slipping in seismic rate. So basically, in this particular snapshot, you are looking at a full rupture of an earthquake on the fault. And so for a tectonic sequence without any external stress perturbation, so for the first simulation, I'm not changing any of the pore pressure, you can see that there are cycles of earthquake generated on this fault. And each of these earthquakes has a magnitude of about 3.3 and with a pretty average stable stress drop of about 4 megapascals. So this is like the unperturbed case. I have this nice repeating earthquake sequence occurring. But what I'm going to do next is I select one of the seismic cycles, say the one that I'm highlighting here, and I perturbed the pore pressure during this particular seismic period, seismic cycle. And I basically perturbed it in different ways. I try to change the pore pressure magnitude, and I also try to perturb at different times during the seismic cycle. So sometimes the perturbation occurs very early on, and sometimes I perturb the fault at a very late stage of the cycle. And so I'll see what happened. So this is like the main result of our study, which is we talked about like the change in the timing of the triggered earthquakes. So what are you looking at here is the change of the earthquake timing, of the timing of the earthquake that occurred next after the perturbation happened. And here on the x-axis, you're looking at the time of perturbation. So during that interseismic period, when did I apply that perturbation? So if you're looking at like on the left-hand side here, which means that the fault is perturbed very early on during that interseismic period. But as you move to the right, at 90%, the fault is basically close to the next rupture. So what you can see here is this dashed line indicates two categories, separates the two categories of earthquakes. The ones below has experienced a time advancement. So basically it means that the next earthquake occurs sooner than it's supposed to be without, if there's no pore pressure perturbation. But anything above it indicates that the earthquake actually occurs later than what it would have been without any perturbation. And so what we see is most of the majority cases actually falls into the time advancement region, but there are also quite a few cases that occurs with a time delay. And most of these delay cases is actually corresponding with very small perturbations, say 0.1 or 0.2 megapascal. And what surprises us also is that if you zoom into, the later part of the interseismic period, we also try to perturb the fault at different seismic cycles. And what we see is that some of these earthquakes, even though the perturbation occurs really late during the cycle, which means that the fault is really close to the next failure. And supposedly this perturbation will just, push the fault to failure directly. But instead of doing that, some cases actually, delay the next earthquake for up to 10%. So this is especially surprising. So if you zoom into, what happened actually on the velocity weakening region for different cases, some with advancement, some with delay, we can look at, how the fault is responding in terms of slip. So here I'm showing a figure that shows the seismic moment and the aseismic moment release on the weakening region on this like seismogenic patch. And what you can see is that the seismic moment would experience a vertical jump whenever there is an earthquake. But at the same time, you can see that the aseismic moment is gradually increasing throughout the interseismic period. And this is because the seismogenic region is not completely locked. It has experiences, creeping. Different extent of creeping throughout the interseismic period. And so you can see here, 8.1 megapascal of pore pressure is applied at 85% of the cycle, as indicated by this dashed line. And right at the moment of perturbation, actually, if you look at the seismogenic patch, most of it is already not locked, is already slipping at a, close to the background tectonic loading rate. And once the perturbation occurred, it just, continues to shrink the locked region. And eventually, an earthquake got triggered at day 20 and day 52. And if you compare it to this gray line, this gray star, which is the unperturbed case, you can see that the new earthquake is advanced by, a certain, a number of days. But at the same time, if you look at, a delay cases, things are a lot more complicated. Here we have a 0.1 megapascal pore pressure increase at about 80% of the cycle, so also pretty late. But you can see, a very different response. So here, right at the perturbation, you see actually in a creeping episode that occurred right after. So if you look at the snapshot of, the number 2 that I indicate here, you can see that the slip rate has picked up a lot within the seismogenic region as indicated by this yellow color. So it's a lot faster creeping than compared to the background loading rate, but it's not, in the seismic range yet. It's not fast enough to be radiating seismic energy. And so after this episode, the fault actually returns to a pretty quiet state until the next creeping episode, which is smaller, but still, like you can see that a large part of the seismogenic region is creeping, is picking up the slip rate. And afterwards, the fault, returns to a partially locked region, a locked status again, before finally in day 184, you see that there is a huge earthquake generated on the fault. And again, if you compare with the unperturbed case right here, there is a time delay for sure. And so what we find is that if we look at the timing of the change in timing of these earthquakes versus the aseismic moment release, so versus the moment release due to creeping, you can see a positive correlation. So what I mean here is that this is the line that separates the two categories: events that experience time advancement and events that experience time delay. And you can see that the time delay cases has a much larger aseismic moment release compared to those with time advancement. Especially if you look at these two cases with the most amount of time delay, you can see that they're associated with the highest amount of aseismic moment. And these aseismic moment is actually comparable to moment released by an earthquake with an average size of a 3.3. So these moments itself are released over a much longer period of time, but it's the total amount of moment is actually equivalent to a typical earthquake on this fault. And so the question that we want to ask or want to quantify would be what's the actual role of these aseismic transients? Can we actually quantify their behaviors and be able to tell something about the outcome of the next earthquake? So we examine the frequency and the intensity of the triggered aseismic transients. And here what I'm showing is an unperturbed case. So imagine there's no change in pore pressure. And this is like one of the cycles that we observe. And you can see that, these are the two huge events, earthquakes occurring on the fault. And this is the interseismic period. And you can see that the aseismic moment steadily increase through time, until it, reaches pretty late in the cycle when it picks up slightly in the aseismic moment release rate. But basically this is the aseismic and the seismic moment release, and this gray line indicates the maximum slip rate in the on the fault. And basically you can see that for each of these earthquakes, it associated with a huge jump in seismic in slip velocity up to like the seismic ranges on the order of meters per second. So if you look at cases with an earthquake advancement, time advancement, what you see is that we observe a critical slip rate that associate with these events, which means that if the slip rate did not elevate beyond that critical slip rate, we will see a time advancement of the next event in general. So what I mean is that here, the perturbation occur at 60% of the cycle. And you can see that, the slip rate elevate right away because there is a creep episode. But the slip rate elevation is pretty small. It's just by about 2 orders. It's less than the 5.5, 10 to the minus 5.5 meters per second. And so you can see in this case, the next earthquake is actually advanced. But on the other hand, if you look at a slight difference in the perturbation with also 0.2 megapascal, but if the perturbation occurred early on in the cycle, you can actually see that there are a lot more aseismic activities going on with these different episodes of elevation. And one of them actually elevates all the way to almost 10 to the minus 2 meters per second, which is higher than the critical rate. And you can see that there is associated with a huge aseismic release, and the next earthquake is actually delayed. So to summarize this part of the finding, what we see is that even very small perturbation of pore pressure can induce substantial aseismic response. And this is the aseismic response indirectly change the outcome of the next earthquakes, which means that it can change the earthquake recurrence interval. Some it can delay, some it can advance. And especially the delayed trigger cases are associated with large aseismic moment release. So what I mean here is that there was usually a lot of creeping triggered before an earthquake that is usually delayed. And so the important implications here in the context of induced earthquake is that people usually believe that if you reduce the injection operations, if you reduce the amount of water injected, you would soon see a drop in seismicity rate because they are associated. And we do see that in finding, people try to slow down the injection, and then we do see a drop in number of earthquakes. But this finding suggests that, there are a lot of earthquakes that are waiting to fail on a fault, but they're delayed because of these aseismic motions. So in a way, the phenomenon of this, induced earthquakes could last for much longer than expected, even after the reduction of the operations, because a lot of them are actually delayed and we're still waiting for them to happen. And another thing is, with enhanced instrumentations and monitoring, we can potentially identify fault-specific critical conditions that can determine the outcome of triggering. So if we know, a fault really well, how it's, responding, how it slips aseismically, we may be able to monitor, the evolution of the aseismic part and be able to predict or forecast, in the future, we might be expecting an earthquake that is occurring, soon or, later. And so this is like the study that I want to talk about today, and this is the main results. And I'm just going to introduce quickly, the courses that I'm going to teach next term before, I will open the platform for any questions. And so here, basically, in winter 2021, I'm going to teach a course, a third-year course in geophysics. And so basically, apart from just earthquakes, I'm also going to talk about like gravities, magnetism, heat flow, isostasy, topics like that. And we are going to learn different, geophysical equations that can address these real life geoscience problems. And so this is just a globe, showing you what are the waves that can propagate outward from an earthquake source, and how we may be able to use these different waveforms to understand the internal structure of the earth. So that's one thing that we'll study in this course. And the other course that I'll teach is ERS 101, which is Planet Earth. It's an introductory geology course. And so if first year students who may be interested in learning about geology and even like considering geology as a major, so definitely encourage them to take this course. And so I guess I will open the floor right now and just answer any questions that you may have. So thank you very much for your time.
Thank you, Semechah. That was a really great talk. That was really interesting. I do think we have one question from Mohammed. Are you able to see the chat?
I don't think so. Should I stop sharing right now, or
no, you can keep it if you'd like.
Okay. Okay.
I guess I can just read it out.
Actually, I can. Let's see.
Okay.
Does the rate at which the fault slips and friction opposing it is 1-to-1, or is it more like drag where the friction is increasing quadratically? Do we use them both in conjunction depending on the status of the fault? Sorry, let me read it again to see if I understand. So I think a little clarification. Basically, what I mean is like under the rate and state friction laws, the frictional parameter itself is dependent on the rate. So actually, one description of it is like if we see this direct correlation between the slip rate on the fault and the friction. So what it means is that you will see if the fault experience like a step jump in terms of velocity at the slip on the fault, you would actually see a jump in the frictional parameter as well. And so it will become more frictional. Well, I guess it will become more frictional strengthening in the case that I just described. So let's see if I understand. Yeah, so I don't know if I understand answered your question. Do you want to clarify, Mohammed? Oh, okay. Yeah, I'm actually hosting a RP student this year. So we are working on understanding earthquakes using a community seismometer called the Raspberry Shake. So what we have purchased recently is a community-sized seismometer that we are actually installing it at UTM earlier this year, but I actually recently moved it to my home just because it's easier to monitor it that way since I'm working from home. But these are like community used like widely around the globe. And so right now, what people are doing is like using this little seismometers. We are building what we call a seismometer, a respiratory shake network. And what we are studying in this project is to see how this network performs compared to the research grade network that people have also installed throughout the world. And so what is exciting is actually, I don't know if you remember, but there was a magnitude 7.5 earthquake that occurred in Alaska a month ago. Yeah, and we are actually able to record that on our little seismometer here in Mississippi. I live in Thornhill, so in Richmond Hill area, and we are really hoping, that we'll see more earthquakes. I always feel like conflicted, saying this because I don't want any, major hazard or destruction occurring to any cities or any crowded areas. But, and I'm glad that the one that we recorded is in Alaska, which I don't think, created a lot of damage or casualties. So I yet to, from yesterday, we can any of the 6 earthquakes in Southern America or in Russia, but I'll do that later today. Eric, was there any sort of errors between? I don't think there's an error, but I think what is interesting is, well, not interesting, but what people find from previous study is that the respiratory shake, the community seismometer may not be as sensitive as the research ones. So for example, we may need a stronger signals before we can detect that is actually an earthquake. And also we may have a slightly higher uncertainties in terms of determining the magnitudes of the earthquake. But in terms of detecting an earthquake and identifying, these are like actual seismic signals, I think they are recording very similar data. So I guess the only difference is that, the community seismometer is not as sensitive as the research ones. Yeah. How can we, for this year, I'm not opening new spots. I have one RP students already, but next year, I think we will probably continue this project, and also I will be recruiting. So let's see, it's going to be a year-long project. So I think can some, other 3rd or 4th year students help me here? I'm not sure when the application will be open, probably in May, when you can register for courses. I think you will also be able to apply for the ROP projects. I think I usually receive applications around April and May. Yeah, around April and May which will be in 2021. And then I will, be able to pick students who, qualifies to work, with me. And then the project will technically start in fall 2021 in this case.
Semechah, did you want to talk? Are you still teaching that earthquake seismology course in the following years?
Yeah. So basically, I alternate ERS 303, which is geophysics. I alternate that with ERS 403, which is earthquake seismology. And the earthquake seismology is basically a course that focuses on, using seismic data and to understand, earthquakes and different properties of earthquakes, basically. Apart from what I talk about, which is magnitude today, we also have other properties such as, focal mechanism, which you might have heard or learned in your 1st or 2nd year courses in planet Earth or in tectonics or in structural geology. Structural geology. And also, we are going to learn about how we use seismic rays to not just learn about the earthquake sources, but also the how to categorize the internal structure of the Earth. So there will be topics on, characterizing earthquake sources, understanding, say using seismic tomography to understand the Earth structure, and also earthquake prediction and forecasting, what people have done so far and whether we're successful or not, and seismic hazard mitigation plans and all that. So it'll be a much more focused on seismology itself, rather than for geophysics course it will be more on like different kinds of geophysical data. I'm wondering if we look at oil and others. Yeah, so we'll actually look a little in seismic exploration of oil in Geophysics 303 when we talk about the topic of, when we get into the seismology topic of that course. But I think I would talk more about like exploration of oil in, the 403 course, which, it's actually part of understanding, in how we use seismic data to understand the internal structure of the earth. For the part of, oil exploration is probably we're focusing on the shallow crustal region, and less about, the mantle or the core. But it's effectively using seismology to understand structures. So we'll definitely touch on that in 403.
All right, awesome. Does anyone else have
Mhm.
further questions? I'm gonna assume that's a no for now.
Okay.
So Semechah, thank you for
Yeah.
your talk. That was wonderful.
Yeah, you're very welcome.
And thank you for taking the questions.
Mhm.
It's very appreciated. And on behalf of the Geology Club at UTM, we appreciate it. We will be posting this on our YouTube, just if
Okay.
anyone's ever curious. And we
Yeah.
do link the videos and the seminars into our weekly emails as well. So thank you very much. Thank you for your time.
Yeah, thank you all for attending. So I hope to see some of you, in my future courses.
Yeah, I hope so. I hope so.
Okay,
Thank you,
have a great
Semechah.
day, everyone. Okay, bye-bye.
You too. Thank you so much.
Yeah.